Oh, yeah.
Everyone. Today, we are learning x86 assembly. Woo. So, very exciting. I know x86 is one of the languages that I actually am very excited and happy that I've learned due to its benefits to understanding memory and memory management, specifically at low level. So here's who I am. I'm Julius. I'm a computer science and an econ student. So I'm finishing up my double degree this semester, and I'm graduating in December. An admin, and I can windmill dunk a basketball, where you like dribble, and then bring it down, and then you dunk. So that's who I am. And so here's the little XKCD, and then the meeting flag, and then we can get started. I'll kind of be talking a little bit about the meeting flag. It says Roller Coaster Tycoon. So very excited. Yeah, I actually haven't read the XKCD. So I will read it, you guys into the flag, and then we can continue.
Oh, that's a good one.
What's the butterfly? Real. Oh, okay. I think I've changed and added the flag at the end. I'm not sure though. Focus more on the actual content. But x86. I guess actually announcements first. Amateurs was canceled, so our new plan is to have a pizza and game night in Siebel on Friday, and we'll send announcements for that, as well as our first lockpicking social on Monday at 7 p.m. Anybody who came to the lockpicking social, you can still finish some of the challenges if you would like, and you need to go to lockpicking social if you want to finish the challenges. So,
Dude, yeah. It's like an 8 days. Count them.
Yeah, Monday the week after. So be there. It'll be fun. And MS cool. So now, what is assembly? Does anybody want to say what assembly is, or anybody want to talk about their experience with assembly? Who here has seen assembly, or who's seen assembly before? Okay. Well, I guess now that you've come to the meeting, everyone's hand should be up. But then, but who's written assembly before? Has anybody written some? Oh my gosh, we have so many engineers. Wow. Who here's Compy? Oh wow. Okay, so we have you. By the way, raise your hands higher. I can't see. Okay, so you three. Wow. Who's C? And then everyone else CS. Then I'm assuming. Okay, CS. Okay, CS gang. Who has taken 233 yet? CS 233. Okay. So you guys have done a little MIPS. Okay. What about who's taken EC 220 or 120? Okay. Okay. So some of us have experience with the lower level development. Who's taken 391 or 341? EC 341, CS 39. Okay. Perfect. So assembly is effectively just a human readable abstraction over the CPU instruction code. And so really at one point in time, this code was abstracted. This was our Python. Python was it was wow, this is super easy to read. It's so much nicer than doing ones and zeros. We can actually write code now. And so this is an example of a C method, and C actually compiles down to assembly. So this is what it compiles down to, or this is what the equivalent logic would be in assembly. And so you kind of see here, no pun intended, you have about 5 lines right here, whereas you have a lot more than 5 lines. And so assembly really is going to require you to be a lot more verbose in the way that you code and the way that you kind of think through problem solve. So the basic structures that we have are the instruction memory, which is kind of where we are on our RAM in terms of the memory. And then just specific function, or I wouldn't even say function calls, but really this is where our instructions are going to be executed. Then we have our registers. Registers are similar to variables. So you kind of store information in a variable, and then you can access it at a later time. And then we have our stack. And so for the CS majors that are in here, I would definitely suggest that you focus a lot on how you're managing a stack, because it's very different than something like Python or C or Java, where you don't really have to worry about underlying memory. I guess in C you might have to, but in Java and Python and a lot of abstracted higher level languages, you don't really have to care about how this stack is being managed. And so a lot of the visualizations in this presentation are going to try and help us understand what it means to manage the stack, as well as go through and use our instruction memory and our registers correctly. And so instruction memory is literally just where your programs live in RAM. And so it's read and execute so that we have so that we're kind of secure. We have our instruction pointer, and so this is the first register that we can kind of see. And this is literally just like, think like if you had a long line of tape, like ticker tape almost. And you just take in one thing and you read it, and then you take in another thing and you read it again, and you continue to go down this line. That's what your instruction pointer is doing when it's processing and giving you information to kind of execute a program. And so then simply instruction memory is just RAM that holds your program's code. CPU will fetch it, execute it, and then move on. And so that move on aspect is what that instruction pointer is doing. Also, one other thing is that it's sometimes called a program counter. So for example, if anybody who's taken 233, they talk about this in it's like the PC, like your program counter. So that's a similar idea and pretty much the same thing. So then you have your registers. Registers are going to be places where you hold information, and you can act on this specific system, which is an x86-64 system. These are 64-bit registers. And so you have 16 general purpose registers, as well as 2 that are going to be very, very crucial for us managing our stack. And that is the base pointer and the stack pointer. Yeah. Those are really important. And it's funny too, so for anybody who's written assembly before, did you use R or did you use E? Huh? You did? You used dependent. I remember when I was taking EC391, I used E all the time. So that when I was reading through Sam's presentation, I'm like, R, what's R? It's just a 64-bit system. But this is what the registers look like. And then I was using E, so I was using like EDI, ESP, EVP. And these are the sizes of the registers. And so really this means that we're just going to be holding a certain amount of information in each register. Did I skip anything from here? No. Perfect. The stack. Oh my gosh. This is complicated. That's a stack. That's like your little RAM. Up here you have like kernel memory and kernel space and its memory. And then you have all of your code and your globals, and then where your code is actually going to be holding information in memory. So for example, if you were to run a program that's 10 gigabytes and you only have like 6 gigabytes of RAM, and the program uses 10 gigabytes of RAM, then you're not going to be able to fit all the information that the program actually wants you to use. And so your computer will crash probably, or it'll run really slow, or it just won't work. And so the stack really is just a region of memory that's going to be dedicated to dynamic memory as well as local variables within each program. And so I want you to think almost like, and I think I have an example soon, but really, as you're writing even Python code, the variables that you're using are just going to be stored in some sort of register in a memory address. And at the underlying, the underlying motive is the fact that assembly will expose you directly to this, whereas higher level languages kind of abstract this out, and it improves the development speed. And so this stack also is just the same as any other data structure. So it's last in, first out, and whenever the stack and heap meet, this is kind of where you see like a stack overflow, or you can get this is when you see like a stack overflow. And that's when the heap or the stack grows and then it meets the heap. Also, funny thing for the admins, how many people here know what Stack Overflow, the website, is? Please raise your hand. Some of you guys do? Okay.
Well,
Dude, it's all ChatGPT, bro. And the worst part too is that like when you start to write assembly code, because ChatGPT was like at like 3.5 when I was taking 391, and we would just like try to use it, but there's just not enough assembly out there. So you guys need to write more assembly so we can train our LLMs to write assembly for us. Yeah. No, I'm messing with you. And so yeah, there are two registers, RSP and RVP, which will hold information about our given stack. So the base pointer is going to pretty much define the scope of a given function. So everyone here kind of understands how a scope works when you have a function, right? Like you have a function, and then within that function, you do some sort of logic, and it's within a specific scope. Well, that scope is just everything below a certain base pointer. That's all it is. And so if we kind of go back here, if our function is like right here, then the scope, if our base pointer is right here, is just all of the stuff on our stack that's above it. And that's kind of how you get scope from a function. Then we have the stack pointer, which is going to be the top of our given stack. And so if you have anything in, like everything in between the stack pointer and the base pointer is just within the scope of any given function. And this gets really complicated, especially because you're dealing directly with memory when it comes to having nested function calls or recursive function call, because you start to stack up on like, or I guess stack up this stack, and you keep building and building and building and building. And that's kind of where you get like a stack overflow from a recursive function, or you might see like, yeah, it's just really complicated. So we're going to go through it. These are the local variables, kind of like we had said. Actually, I guess we should start from the bottom up. So whenever you have a function, so if we had our main function, we would push on the arguments first to our stack, and then we would push on a return address. The return address is just the line of code that you're going to go back to when you finish executing whatever function you're trying to do. This is the line of code you go back to. This is the scope of the function that you go back to. And then after that, you start to use local variables to do logic that you would need. Without these three things, we would just have logic in our given spot. And so this is not a good example because we go deeper into it. And I kind of want to address the fact that these are two different things. And even when I was making the slides, I felt like it was kind of complicated to what's the difference between like a save base pointer and then a return address. Well, we're going to go through it. So if we have a main function right here on line 9, well, first off, I guess I'll take a step back. The saved base pointer is just the scope of the previous function. That's all it is. So if we're in the main function, our base pointer should point to wherever the start of the scope of the main function begins. So if we were to have a base pointer, it would point to line 9. And that's kind of like what's happening right here. You were running the main function. Then our return address is the line in that scope that we want to return to. So when we go into the helper function, we want to return to line 11. And that is going to be this saved, or that's going to be the return address. And so if we were to start on line 9, go down a line to line 10, and also when we go through this code, it's almost like we are the instruction pointer or the program count. And so we go down a line, and we go into helper. But before we go into the helper function, we need to set up our stack. Because even if we were to just move straight to line 3, we wouldn't have any information about where we need to go back to. And so what we do is we push 3 on, which is our argument. Then we say, after we know what we're going to bring wherever we're going to, we're going to now push wherever we currently are. Then we're going to push wherever we're currently in, so the main function. And then we can move to the helper function and start by pushing temp 6.7. And then this is a breakpoint at line 5 that I did. So we kind of broke at line 5, so we're at that current state. But this is what our stack would look like before we run line 5. And yeah, I hope that that kind of clears things up. It's really complicated. One thing I do suggest as well is if you have a lot of questions, ask ChatGPT, like high level, what is going on, especially with the stack, because stack manipulation is very complicated, especially if you haven't been exposed to it before. And so here's another example where we have a method and we are at, I think we're right before the return. And so in this method, we have gone through and pushed B, pushed C, pushed D, and then returned that value and put that into a certain register that's going to be returned. And then we've gone through and pretty much, this is what our stack would look like before we return A plus B. Does anyone have any questions that they want me to answer at all? And feel free, there are no stupid questions when it comes to x86 assembly. Like, this is very difficult, and there's a reason that x86 assembly developers actually get paid a lot right now. It's because you can't ChatGPT this. At least you can't ChatGPT it if you're writing it. You can kind of understand what's going on. But I've tried. It's hard. But yeah, this is one other thing that I want to note is that the RSP is pointing to the top of this stack, and the base pointer is pointing to the beginning of the scope of that given method function. And so now the question is like, oh yes.
What's the point of the RBP if you already know which line you're going to return to? So if you have RBP and if you don't have RBP, then go to the
Yeah. So the real reason that we have RBP right here is because this is the scope of the current function. And so we can think of method one of being called from some other function. And especially when we start to run a given program, we start with like the most broad scope, and then we run our main function, and then we run other things. Like think like you run it on like your operating system, and then you run a program on your operating system. And so returning to this base pointer is really just going back to the scope of the broader function. So think of method one being ran in main. Save base pointer would point back to main's scope. And then the return address would point back to the spot in main that method one was called. Yes.
What are like the key differences between x86 assembly versus like MIPS assembly?
From what I've experienced, I feel like I know MIPS assembly abstracts out the stack a lot more. So x86 throws you right into the fire, and you have to manage stack explicitly the entire time. If you don't use certain registers, I believe, in MIPS, you kind of can get away with the stack management and not really have to worry about managing stack until you are using and creating more complex functions. Yeah.
I just want to bring up briefly, x86 is also a complex instruction set, so there's just a lot of instructions than left registers. Compared to MIPS has less instructions and a lot of registers.
Yeah, great point. And then, yeah, and kind of a side note on this, I remember when I was taking 391 and you had to write an x86 before it became RISC-V. They gave us the like instruction manual that's like 900 pages, and they're like, yeah, like you got it, like learn it, you got it, like don't worry. And I'm like, bro, like, and I'm control Fing, and I'm like seeing the for loop go down the file. I'm like, dude. Yeah, so awesome questions, guys. Thank you. So now there's a note on syntax, because multiple people have written x86 in different ways. It's not that much different, especially if you were to switch from any given one assembly language to another one. I mentioned RISC-V being the current EC391 assembly language. But before that, it was x86, and I know their first semester CAs and TAs were kind of freaking out because they were like, they hadn't done the MPs before, but they actually understood assembly really well. It's just that the actual implementation of it is really, really in depth and really requires a lot of attention to detail. And so here's XKCD. You'd be surprised how often I reference this XKCD. Like more than I thought I would. And so here are the two types of syntax. AT&T has the percentage sign. Comments are a little different. I'm not sure, do you guys know if the execution like is different in terms of like which one is executed, in terms of like, is RSP executed? Or is this the destination, or is that this? I don't know. I'm pretty sure that RSP is the destination, but I'm not sure if it's different between both of them.
I'm one of them.
Yeah, it's flipped. They're flipped. So like, keep that in mind.
AT&T, I believe, is destination on the right.
Destination is over here, right, AT&T? Yeah.
Oh wait, sorry. Yeah.
Yeah, my bad. I can probably. Yeah, so you'll get familiar with it. Really, the difference between a destination and a source isn't as important. And then manual retyping. And this is kind of the idea of how this would work. So you have a mnemonic, a destination, and a source. So for example, if we wanted to add RBX and RAX, we would take RBX as register, we would add it to RAX, and then where would it go? Well, actually, it just goes back into RAX. And so we have specific ones here that are nice, like we have a shift left on RCX, a multiply using 3. So we multiply this R10, X20, and put that in R8. Does anyone know what this is, this XOR on our side? Yes.
I think it's a trick they use to zero RSI, because there's no good way to do it otherwise.
Exactly, yeah. That is that's very true. So this is a trick that you can use to zero a register. And it's actually a lot faster than assigning 0 to the register. One note on this, if you were to do this in Python, the interpreter would just optimize it out, and because they do that. Like if you assign 0 to a register in Python or a value in Python, they do this under the hood. So you just kind of look like a prick if you just add an XOR in there. So don't do that. I guess you could, but like you kind of like, it's like, dude, okay. So what, you came to Julius's assembly talk, okay. But yeah, and then here's a subtraction. So you subtract dx. Yeah, but keep this in mind, this ordering. This ordering is pretty interesting. And then now we're going to go into some examples. So the interesting thing about assembly is that we are this instruction pointer going through and executing line by line our assembly code. And so one of the things that you may have a question about is like, how do we have loops? Like, how do we make for loops and while loops and change into different functions and things like that? Well, what we do is we use this jump command. And so we can jump directly to different parts of our program based on their number or their counter, things like that. And so what we do is we use labels, and we'll put a label on, and then we'll be able to jump to that label in order to execute new things. And I love how Sam kind of put, this is one of the ways to modify a rib, hopefully safely, because that's real. Like you can just jump. And then another thing that we have compares. So our conditional statements are comparisons where we kind of compare if they're 0 by subtracting them, or if we get a positive, it's like a compare with A is greater than B or A is less than B. And compare is just subtracting the registers and then setting the flags so that we can use them later. And then we'll jump if this ends up being true, and then yeah, if the condition is met, then it'll be based on flags set by that comparator. And so here's an example of assembly code. And so what we do, we're going to kind of walk through this, and I have other slides as well that kind of explain this in a more simple term. But, or I guess, does anyone want to give it a shot and explain or try and explain it at all? Because I can do it, but it'd be more fun if somebody else did it. I can do it. It's okay. This is the first example. So we move 32 into RBX, and we move 15 or 21 into RAX, and then we have this label. After this label, and the labels don't actually do anything. They're just locations. So then we do a comparison on RAX and RBX, and we see if the difference between these is equal. And if they are equal, then it'll set the flags after we do this comparison. And we have this equation, which is jump not equal. If they're not equal, then we jump to bar. we XOR RAX, and then we return. So if they aren't equal, given that it's 31 and or 32 and 21, then we jump to bar where we decrement RBX, then we move back to foo. And so we continue to do this. So 32, go compare, jump to bar, 31, 30, 29, 28, 27, 26, 25, 24, 23, 22, 21, where it doesn't jump, we XOR RAX and then return. So what this does is it pretty much just, if RBX is greater than RAX, we're going to pretty much get it to RAX and then clear RAX. This is kind of what you do in Python. So we have two different variables. We have a while loop where they're not equal to each other. We subtract, 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 and then we will return. This is a lot nicer to read. But we don't have that without this. Because at one point in time, this was the only option that we had, which is kind of crazy. And I'll kind of get into like one really cool example at the very end. But, and it's funny too, actually, because we have about like, how many lines is this? 1, 2, 3, 4, 5, 6, 7, 8, 10. We have 10 lines here. You could probably like 2-line, 3-line this. Like, you could definitely combine first and second, and you could probably get a while loop in 1 line and then return. But the cool thing that's assembly has that other higher level languages don't have, and I don't know if it's, I think it's cool, but I don't know if you guys would think it's cool, is that we just return. Like, we don't really do anything. Like, we kind of just return. And so if we were to directly translate this, we're just returning here. But in Python, returning like this doesn't matter, because once we leave this scope, all this is gone. And that's the really fundamental difference between x86 and Python, or a higher level language like Java, where just because we're in this scope doesn't mean that the registers that are actually existing under it are going to be changed or are going to stay. I think, you know, just because we're in this scope or we leave this scope doesn't mean that these registers are changed, specifically in this example. Like after we leave, RAX is going to have a value, RBX is going to have a value. And this kind of defies some practical like implementations of x86, because you wouldn't want a return value in like RBX, you'd want it in RAX. But for this example, we're holding information in one of the registers, and when we leave the scope of our function, that information still exists, which does not happen in Python. And so, if we wanted to have persistent storage, because right now, like if you go back to this example here, we return RAX, but when we return back to our parent function, RBX is going to actually be, it might be overwritten. And so if we kind of go back to the registers real quick. AX, BX, CX, DX are all, think like temporary registers. Whereas SI, DI, SI and DI are persistent registers. So usually when you go into a function, you want to make sure that ESI and EDI stay the same as when you entered into that function. And so one of the techniques that we'll do, and this again appeals to that stack idea, is we're going to push onto the stack RDI before we change it. Why would we want to push onto the stack RDI before we change it? Yes.
Oh, we save its value before the function starts, so that we can call it back again.
What did you say?
We save its value before the function is called, so that we can call it back again.
Let's go. He understands it. He's the compy. He understands it. Exactly. So what we want to do is when we push on RDI, we're practically saving that value on the stack for right before when we return, we'll then fill it back in. And this allows us to keep the same information while still using that register. And so that's the big thing, is that we want our return value to be in RAX, but if we're using RDI, we don't want to overwrite that data. And so we can push on different information. We can pop different information off of the stack. Underlying this is the logic. So we just move a register into RSP and then decrement RSP. One thing to note as well is that the stack pointer grows down in our stack. I don't know if anybody noticed that. The stack starts at the highest level and it slowly decreases. The heap will actually increase. And so if we want to add something to our stack, we'll decrement it. Same thing with pop, except in the inverse. And so push and pop are just ways that you can push onto the stack and take off. And so here's a visualization of this, where we start with RAX, where we move leak code into RAX. Then we push it onto the stack. We zero RAX. And then we take off of the stack and put it into RBX. And this is an example of us using the stack to kind of keep information. And then we have this idea of syscalls. If you take an operating systems class, you're going to learn that there are different privilege levels in your operating system. There's a user space and there's a kernel space. In the kernel space, you can do a lot more critical functions. So think like reads, writes, executing programs. Whereas in the user space, you're not always able to do that, and you will get like privilege. You'll get blocked pretty much. And so one of the examples of this is glibc. If you've used it, glibc has some wrappers that kind of allow you to do syscalls. And in assembly, you actually are required for doing the syscall. So what you'll do is you go up to the ABI table and you'll find the number that is associated with the given syscall. And like, this is kind of crazy because it's not a name or anything like that. It's just like a hex like number. And you would load it into your arguments, the given information for that syscall in these specific registers. You'd use the syscall instruction, and then you would get a return value, hopefully in RAX. And so these are examples of syscall. This is an exit syscall, and this is an exec or execute syscall. And this goes through the process of pushing on this stack, and then, or actually, no, not even pushing on the stack, loading the registers, and then running syscall, the command. Here are pointers and dereferencing. So registers don't just hold values, they also hold memory addresses. And so what you can do is you can actually decrement these registers, or you can dereference these registers in order to get the values that the registers actually hold. This is a great, this is very useful for iterating through arrays. And you can also write to memory the same way. So, hold on. This is the cool part about this talk. And I need to emphasize this to you. Everybody. Does anybody know what this is? Yes. Or no. You're a health program. Yeah. Does anybody know what this is? Yes. Roller Coaster Tycoon. This is an amazing game. And it's amazing for a lot of different reasons. They have dynamic pricing, pathfinding, ride physics, game logic. It's a great game. I played it a lot when I'm a lot. It was awesome. It ran on every computer, or at least all the x86 computers. That's it. And sold millions of copies. It was awesome. But as I grew and I realized how much I loved x86 or how much I loved Roller Coaster Tycoon, there was something that made it even better. It's all an x86 assembly. And so yeah, Roller Coaster Tycoon was built entirely in x86 assembly. And I needed to get on the table to explain that because that's very critical. And it was amazing. Like this guy, Chris Sawyer, wrote x86 assembly to do all of this previous stuff. Like imagine implementing a pathfinding algorithm or dynamic pricing using what we just learned today. In theory, you guys can do it. That's our challenge on it. But in general, like understand that this is such a big feat. Like this is amazing. This is so crazy. And it ran using such low amounts of memory that you could actually create a game like this. Like this has like 5 different roller coasters. Like you could create so much on such little amounts of memory, and it was so optimized because of this. And so it was just amazing. And like I wanted to add this to the slides because I thought it was really cool. And yeah, so here are a few resources that you can use to kind of understand how x86 works and how important these are. Pretty useful, especially the online assembler, to actually run x86. And then here are a few challenges that we have. Please use Pwn tools. It'll be helpful for the challenges. And then we have a meeting this Thursday for Rev, and then amateur CTF this camp. So hopefully you guys learned a little bit about x86 assembly. I know it's such a complicated topic, and there's just so much to digest and assemble. So yeah, that's the presentation, I think, yeah. So thank you guys for coming out to x86. Does anyone have any questions at all? No. Has anybody played Roller Coaster Tycoon? Even if you haven't played the original one, have you played anything similar to it? Zoo Tycoon? Oh, Roller Coaster Tycoon 2? Okay. I played Zoo Tycoon. It was really fun. But thanks guys for coming out. Thank you.
Yeah.
Go solve the challenges on FA2025 CTF. We have a few. They're just basically very we're not going into anything like security related. It's just like kind of teaching you assembly writing. And if you felt overwhelmed by the content, because there is a lot, don't be, because like eventually in your curriculum you will take systems programming, and you'll learn the courses here will teach you assembly better than we can teach you assembly.
Yeah.
So like don't worry about it. But if you do engage with this now, you'll have a much better, easier time in those classes as well. So
Yeah.
consider
it an investment.
Work like that.
x86 is setting in. So yeah, I think the Zoo Tycoon, and I watched a video on that too. I was like, they're like, and it's funny too because they don't really have like YouTube shorts of the whole thing. It's like it's just straight like 60-minute videos, like documentaries practically on like Zoo Tycoon.
I saw like a video like last night. I was listening, just going to YouTube, and I was like, I'm pretty sure this is about Roller Coaster Tycoon. Because it's called like Why You'll Never Be Another Game.
Exactly, bro. Like the clickbait.
Yeah, like where I'm like why there'll never be another game like Roller Coaster Tycoon. I'm like, Planet Coaster already exists, so the only thing this can be about is x86.
Exactly. It's so funny. Well, I guess actually we can go back to the.
The local, they put